Manga, you can start.
I'm glad to invite Dr. Ankita Khatri on behalf of VCAN 2020 to present her work on ab initio modeling of the role of defects in thermal transports. Dr. Ankita is the DST Inspire faculty at Center for Modeling and Simulation, University of Pune, India. Prior to this, she was working as a postdoctoral research associate with Professor Nathalie Mingo in CEA, Grenoble, France. She completed her PhD in 2015 with the prestigious Max Planck Fellowship under the guidance of Professor George Madsen and Professor Ralph Datz in ICAMS and Max Planck Institute. Her research interest revolves around the computational study of transport properties in technologically interesting materials, method development to calculate effect of different defects on thermal conductivity of materials. She has several publications in well-known physics and material science journal with an H-index of 11. She is also a peer reviewer for several run-out journals such as Science, Physical Review Letters, Physical Reviews B, etc. Yeah. Now, again, I want to invite Dr. Ankita to present her work.
Okay. Let me share my screen. Okay. Thank you for the nice introduction. So is my screen visible now, right?
Yes.
Yes. Okay. Okay, so good morning, everyone. I'm Ankita Khatri. Before starting, I would actually like to thank the organizers, Professor Nirmala Grace and her team, for organizing this conference and inviting me to be a part of it. These 2 days have been very interesting, and there have been really good talks in these 2 days, and I'm looking forward to the other talks as well of today as well. So now coming to my research, what I'm going to present today, I'm going to talk about ab initio role of defects in thermal transport and materials. So this is the research area that I'm working on for some time, for some years, and I have tried to understand the role of defects in thermal transport from different methodologies, different perspectives, which I will try to give an overview in this talk here. And how different work in different. But before that, we need to first understand that what is the role that why do we need to understand defects in materials and why they are so important. Okay, so yeah, defects are basically unavoidable in many materials during the synthesize process, even if we don't want them. Sometimes we want the defects, but sometimes if we don't want the defects, still they are ubiquitous in the material, they are inherent in the material synthesis. Some of them are intrinsic, some of them are extrinsic also, which are present in the material as well. However, defects can not be always problematic in a material. They could be very favorable in the materials as well. If we pull out any different kind of technologies where the research is going on, we see that there are, we can pull out several examples. Like for thermoelectrics, this is a famous study back in 2012, which showed that introducing defects at different length scales, atomic, mesoscopic, as well as micro scale, so we can improve the thermoelectric performance of the material. For the nanoelectronics as well, if we just take the simple example of a diode, we know that we need to dope it with the p-type. We need to have a p-type and n-type semiconductor for even to make a diode as well, for the transistors as well, and like that. So doping is important there as well. For the different other applications, LEDs, solar cells, defects have shown very interesting results there. This is this one particular for the gallium nitride I would like to tell you about. This is from that famous original paper of gallium nitride for which won the Nobel Prize for a few years back. And here we can very clearly see that the photoluminescence intensity at how it is shifted for the case of magnesium doping in gallium nitride. It is shifted from the to the visible range here, from the ultraviolet range here. So yeah, so we understand that the defects are sort of inherent in different technologies, and they are interested for different technologies. But what also connects these different technologies is the thermal transport in these in the materials and the underlying materials. Why they are why thermal transport is important for the case of technologies such as thermoelectrics, where we need a direct conversion of thermal energy to electrical energy. Obviously, we don't want a good thermal conductivity in the material, so that we have good electrical transport and good electrical transport there. So we do need materials with low thermal conductivity there. For the case of nanoelectronics, we all know that we all have encountered the heating of our devices, our electronic devices, and this is because there is a the hot spots actually form in the chips, and the heat is not able to actually diffuse, and which can actually hamper the life of nanoelectronic devices. So that's why in those materials we need higher thermal conductivity for better life and better performance of those materials to avoid those hotspots. So that is why I am interested in the thermal transport in materials, and I'm trying to, we are in our group, we are trying to understand this thermal conductivity in different materials from the ab initio perspective. So when I say that ab initio perspectives, this is we are doing density functional theory calculations underlying for the underlying base. Apart from that, what I exactly mean by this ab initio calculations of thermal conductivity, so that is this thermal computational methodology. What we follow is based on the solution of Boltzmann transport equation in some approximations for sure to calculate the thermal conductivity. This has been implemented in this code ALMA-BTE, which I have co-developed in my previous group. And so again, coming back to the term ab initio, what is done in this code is basically the thermal conductivity is calculated by considering by considering the contributions of each and every phonon mode. Yeah, so the thermal conductivity, which is calculated, sorry, I think the thermal conductivity symbol has it just disappeared from that. So the thermal conductivity which I calculate, the kappa, which is represented with the Greek symbol kappa, that is calculated from two main ingredients in this ALMA-BTE code. So the first is phonon dispersion. We need the information of, as I said, that it sums up the contributions of each and every phonon modes. So we need the information of each and every phonon modes, the harmonic vibrations, the normal modes, which are basically the quanta of the heat energy. So we need information of that. And along with that, we need the information about how these phonons, how these normal modes basically are scattered in the lattice. If we don't have any scattering in the lattice, that means the thermal conductivity is infinite, which is not the case, which we know that it is not the case practically. So we understand that in each material, there is actually phonon scattering also happening in the material, which brings that infinite, hypothetically infinite limit to the finite thermal conductivity. So that's why we need the information from the harmonic vibrations, the normal modes, and the phonon scattering as well. Both of these quantities are calculated from the first principle calculations, from DFT calculations, bridging the electronic and the structure and the phonons. Now, coming back to, again, the phonon scattering part, the phonon spectrum is relatively quick in calculations. If I talk about the computational expenses, what we need for these calculations, the phonon scattering is quite and extensive also because it has different contributions. We have to take care of different contributions in the phonon scattering to calculate the thermal conductivity, to calculate the final phonon scattering for eventually calculating the predicting the correct thermal conductivity. So these contributions include here, as you see the anharmonic scattering. That means the phonon interactions are taken into account. And if we are just talking about the point defects, atomic defects in the material, what I have studied as of now, so we have to take care of different defects which could be present in the material. Obviously, isotopes could be there, vacancies could be there, some antisites could be there, substitutions could be there, and so on. So we have to take into account, depending on the samples and the synthesis process, as well as the doping, what we have, deliberate doping if we have done, we have to include all the defects, all the role of all those defects in this total scattering rate here to calculate the final thermal conductivity. So now, as I said, again, coming to this point, that the thermal, the effect of the phonon defect scattering. So which defects and in what approximations, or how simply we can actually include these defects in our calculations. So the first step is, if we just consider these defects, these point defects in the lattice as atomic mass perturbation only. So that means we are just treating these defects as some mass irregularity in the lattice. That means it's just the isotope effect what we are seeing here. That means if we just take this cartoon here and yeah, if we see that in the whole lattice, if we just have one atom which has a different mass, however, the bond lengths are not changing. All these bonds which it is connecting to its neighbors are not changing at all, and nothing else is changing. It's just the mass here what is changing for this defects. We can work in this approximation and see how it happens and how much good thermal conductivity prediction we can make with this approximation. So this is basically, we'll call phonon isotope scattering, because it's just the mass difference and nothing else is different. So okay, we'll just consider it as mass difference isotope scattering. And I'll tell you about it later, that we use this formulation for the isotope scattering only. Now, this has been, the formulation has been worked by Shinichiro Tamura in 1984, and it's quite famous. And to broadly explain what main ingredients it needs for the calculation of this scattering rate, so it relates to the phonon density of states of the unperturbed system, as well as to incorporate the effect of defects, we need the mass variance, because it's just the mass defect, so we need the mass variance of the defect. With the mass variance, what I mean is basically is summed up in this formulation here, where we have the concentration of isotope. This mass variance depends on the mass of isotope as well as the concentration of isotope. So I are the number of isotopes for that particular species, A is the atom index and all, which atom we are actually working with, and F is the concentration, M is the mass of that isotope, and we are summing over. The total effect is calculated by summing over all the isotopes of that particular species here. So the mass variance not only depends on the mass, but also on the concentration of the defect as well, which makes sense completely. And on a total, this mass variance goes in the relaxation time, as well as the phonon loss also has a huge impact on the in the calculations of this phonon isotope scattering, which you can find how it comes. The formulation, you can find it in this paper by Tamura. So with this, I studied the isotopic contribution in zinc chalcogenides and tried to understand how much these isotopes could affect the thermal conductivity in zinc chalcogenides. In this case, there could be different. There are several other studies like gallium nitride also, and which have shown very huge effect of phonon isotope scattering in the materials to make a good prediction and to be in sync with the experiments. But why I chose this zinc chalcogenides, there is one good reason for that. at nanoscale, it has been shown earlier that at nanoscale, it shows thermal conductivity crossover, which we have explained in my paper here, back in my paper, by different phonon contributions, why this thermal conductivity crossover happens at nanoscale. I'll come to this point later, but right now we'll focus on the isotopic contribution in zinc chalcogenides and what do we need for these, why it is important, how much it is important for the results. So zinc sulfide, zinc selenide, zinc telluride, the family of these materials called as zinc chalcogenides, they are in zinc blend structure. So the low temperature phase so this is basically the classic zinc blend structure. And for the different for zinc selenide, we will just replace this selenium sulfur with selenium, and for telluride it will be just tellurium here. So the first thing what we said that for the thermal transport we need the phonon dispersion. So if you look at the phonon dispersion of these materials, I just have pulled out zinc sulfide and zinc selenide here, and there's a reason for that. I'll just explain. So this graph shows the phonon frequencies as a function of wave vector, that is in particular path of Brillouin zone. First thing we see that there are no negative frequencies. That means the structure is stable. The dotted and the full lines basically are for different exchange correlation functions used in this study. We needed to understand that how LDA and how PB is actually affecting the thermal conductivity calculations. We have quantified this in our paper as well. So here now coming back to the actual thing of the phonon dispersion. So for the zinc sulfide case, we see that, okay, it matches well with the experiments. And the interesting feature what we see is that a big gap in the acoustic and the optical phonon frequencies mode. So for those who don't know about these optical and acoustic modes, so these three modes are down, are basically acoustic modes. That is the vibration of the whole crystal in 3 axis, and then all the upper frequencies are called optical phonon modes here. So we see that there is a huge acoustic optic gap here, phonon gap here, which affects the phonon-phonon scattering in these materials. So if you have bigger gap, the scattering would be smaller. That's the simplest explanation I can give you as of now, which you will figure out if you'll see the formulation as well. For the case of zinc selenide, we don't see this acoustic optic gap here. This is because this acoustic optic gap basically comes from the difference of mass difference of the constituting elements. So Zn and sulfur have different masses. So the mass ratio is around 2 in this case. So that's why we see a bigger gap here. And for zinc selenide, there is no gap because it has almost same masses of zinc and selenide. That is another thing what we need to know. And for zinc telluride, there is a acoustic gap as well, which because it also has a mass difference there. Now, this is the phonon dispersion. Now we come back to the another part, which is basically the thermal conductivity calculation. I'll come to the scattering part as well. So when we calculated the thermal conductivity, this is thermal conductivity as a function of temperature. And again, the full lines are LDA results, dashed lines are PB results. I've scaled down the conductivities of zinc selenide and telluride by a factor of 10 and 100 to be able to see the plots clearly in this figure. So we see that on an average we have a good correspondence with the experiments, and at a bigger temperature range as well. So now with this, we know that, okay, thermal conductivity is the calculations are matching with the experiments. Now we see that these results are basically with enharmonic as well as isotope scattering. Now we see that how much is the effect of isotope scattering in these materials. So when we look at these are the phonon scattering rates that I have pulled out. So the first plot is phonon corresponding to phonon scattering. The scattering rates inverse of tau, the relaxation time, function of phonon energy, H cross omega, and the isotope scattering as a function of phonon frequencies here. We see that that at lower phonon frequencies, the enharmonic scattering, this is at the 300 Kelvin, dominates, and higher frequencies we see that phonon isotope scattering starts to have the effect as well. This is on almost on the same scale here. If we see on a relatively close scale, we can say that here. That is quite interesting. And so we know that, okay, phonon isotope scattering would be affecting the thermal conductivity here to lower down the thermal conductivity. Another important point I want to raise here is that if we see these lines, these basically correspond to the empirical formulation what we know for these scattering. So phonon scattering is known to follow omega square dependence on the phonon frequencies, and phonon isotope the omega to the power 4. But if we just consider those empirical models in our calculations, we won't be able to get these lines. We are not able to understand all the phonon modes or the contributions of each and every phonon modes and all these wiggles around on these lines, which are mainly important if to understand the role of the defects here, because some frequencies, some modes, if they are contributing more, and when they are brought down by one of the competing phonon scattering mechanisms, so to understand that, we need to go out from the empirical formulations and understand it from the ab initio perspective here. So with this picture, we are able to get an idea that, okay, phonon isotope scattering is affecting the thermal conductivity. However, to quantify these effects, I have just pulled out this table where what I have shown is basically for thermal conductivities for zinc sulfide, selenide, and telluride, LD and BB calculations. Again, the first column is the phonon, the lattice constant. So you will get an idea of the volume here, because it will be just a cube in this case. It's cubic here geometry, and then the thermal conductivity ANH here corresponds to that. This thermal conductivity is calculated with just phonon interaction, and then the final thermal conductivity, which also includes phonon isotope scattering as well. This P is a very interesting and a special number, which is basically the percentage isotope factor introduced by Lucas Lindsay. So what it says is that it calculates the effect of the change in total and enharmonic thermal conductivity as a divided by the total thermal conductivity, the final thermal conductivity multiplied by 100, and that's why it is percentage. So it tells that how much is the effect of the isotopes in that particular material. So if we see the percentage, if we just see the numbers here for the case of ZNS, we see that with the enharmonic scattering, it is 37 watt per meter Kelvin. Sorry, I forgot to pull out the units here. 37 watt per meter Kelvin. Then it reduced to 31, and the experiments are something around 27. Even if we don't see that much difference here, if we calculate the percentage isotope factor, we see that there is around 20% of difference in these values, and 20% the effect of the quantified, what we have done, quantified the effects of isotopes. We can say that the thermal conductivity reduces by 20% when we include the effect of isotopes here. For the case of, for the time being, I will suggest we'll just leave LDA results. They are also on the same trends. But we'll just discuss right now the PB results. For the case of ZNSE, we see that this percentage isotope factor, that is the effect of isotopes, reduces here. This not only links with the mass variance, the formula which I have shown earlier. However, it also we can see that there is a link to these values here, KL, ANH. So higher the values we see, higher effect of phonon isotope scattering, and lower enharmonic scattering in the material, or higher the enharmonic scattering, sorry, and lower the thermal conductivity in material, already we see less effect of the phonon isotope scattering, which is a very interesting result here. However, the main thing, what the take-home message here at this point is basically that the role of mastering of that is crucial in determining in correctly predicting the thermal conductivity of materials, and we need to include these defects in our calculations for sure. If the mass scattering is too high, if the mass variance in the materials is too high and all. Now coming to the crossover, I'll just briefly mention about it and we'll move to the other part. So this thermal conductivity crossover, which I told you first, that it is quite interesting we see in these materials, zinc chalcogenides, and what we see here is that at bulk, this is the thermal conductivity plot as a function of grain size, you can say. So for higher grains, that is at the bulk, what we see that zinc selenide and telluride have similar thermal conductivity, this blue and green line, and zinc sulfide has higher thermal conductivity. But when we go to the nanostructure part of it, then we see that zinc sulfide and selenide have similar thermal conductivity and telluride has lower thermal conductivity. This we have explained in our paper by the fact that there are long mean free path phonons contributing more in zinc sulfide and telluride, and when those contributions are taken away, the thermal conductivity reduction at the nanostructures in the nanostructures is quite steep, and that's why we get the this kind of thermal conductivity crossover here. Okay, so okay, I briefly mentioned it, and I think I will just go back to the defects again because we were following that particular sync to maintain that sync. So now what we discussed till now is that mass defect, how if we consider the defects as only mass perturbations in the material, so what happens now? For the cases where the mass perturbations, like we see here, that there are just mass perturbations, I'm just changing a bit of language here because I'm now considering it as a V matrix, which I'll tell later why, is basically the difference in the perfect and the defected state of my material here. So if we just consider the mass perturbation, the perturbation matrix from there, it is just simple. That's what we have seen here. And however, when we have a substitution or a vacancy, we know that the local geometry also changes, which is I have tried to show it here with this cartoon. So those effects also have to be taken into account to understand the phonon defect scattering, actual phonon defect scattering in those materials where there is not only the mass defect present there. So this we have done using we have included this using ab initio Green's function approach, which is actually explained in one of my paper as well as in these two other papers. And with this approach, how it works and how we actually calculate the defect scattering, I'll show the results about it now. So for this, we have studied defects in cubic silicon carbide, and I'll just take an example of silicon carbide for illustrating how introducing the bond defect or including the bond perturbations in our calculations, how does it completely changes the result. So for this cubic silicon carbide, it is very interesting. It's a very interesting material because the silicon carbide actually has several polymorphs. That means it can actually be stabilized in different structures. One is cubic phase, which is again zinc blende structure. The others are hexagonal phases, 2H, 4H, 6H, depending on the stacking of that system. There are several hexagonal, there are several tetragonal phases as well. However, one of the studies actually suggested there are several those which on the silicon carbide. What we saw in the literature is that cubic silicon carbide has lower thermal conductivity than the more complicated hexagonal phase. However, it is not intuitively correct because the hexagonal phases are the more complicated phases, the lower thermal conductivity is sort of a general intuition, and the idea is. So for that, what is happening there, we try to understand whether there are some defects actually playing their role in these materials. So we try to understand it. So for that, first we try to just calculate the phonon scattering rate. Phonon scattering as a function of phonon frequencies for pure silicon carbide. This is the n-harmonic scattering, phonon scattering, and the isotope scattering, the green line here. So we see that the isotope scattering is actually smaller as compared to n-harmonic scattering. And that's what we see in the thermal conductivity plot as well. So these are different experiments for different doped cases as well. isotope scattering is quite high as compared to the experiments. We also figured out that it is actually higher than the hexagonal phases, which we have also discussed in the another study there. So now we understand that there are defects which are playing their role in these materials as well. For that, first, what I did is basically understand these defects, calculate the phonon scattering from these defects, considering these defects, different substitutions as mass defect only. So we now understand what the mass defect is, and when we calculate this, obviously I need to have we need to take care of the defect energetics, that which site is supported for different kind of substitutions which we can get from a defect energetic study on that material. So with that, when we did those proper substitutions and calculated the phonon scattering for a very high defect concentrations, also 10 to the power 20 per centimeter cube, even for that defect concentration, we see that the phonon scattering is quite low, even lower than the isotope scattering. And obviously, this is not going to affect the total thermal conductivity, because the dominant effect would be of the enharmonic scattering, the upper dots here only. Now, when we include the bond perturbations also, so when we do that, the bond perturbations we include in our calculations, we see a drastic difference in our results. So the phonon scattering as a function of phonon frequencies, what we see that for all the substitutions, because of the local change in the geometry, we see that the phonon scattering rates because of these defects are quite high, and obviously they are going to affect the thermal conductivity. And that's what we see in our calculations. And when we include these scattering rates to calculate the thermal conductivity, okay, for the n-doped and nb co-doped cases here, so if we see, we have taken these concentrations from the defect concentrations that was mentioned in the experimental papers, and with those concentrations of defects, when you calculated the thermal conductivity without any fitting parameter, we actually get very good agreement, not only at 300 Kelvin, but for a whole range of temperature for all the cases. So that means this ab initio methodology of including the role of defects from the mass and bond perturbations is quite predictive in nature, and can predict the thermal conductivity in good sync with the experiments. However, now the interesting thing what we notice here is that, what I want to illustrate here is that if we look at the concentrations of the defects, you see that nitrogen, in this case of NB co-doped, boron has lower concentration as compared to nitrogen in both the cases. That means these two samples. However, the shift in the thermal conductivity is relatively quite big. And this is surprising because if you see the periodic table, you will find that boron and nitrogen actually sits besides near to the carbon only, one on the left and one on the right. So why is it such a big difference that boron makes on when it substitutes carbon, and nitrogen doesn't make such a big difference here? So for that, when we try to understand, as it is related to the bond perturbations, when we looked at the bond perturbations, we see that this is basically a plot showing that how the bonds are actually changing, bond lengths are actually changing. So wider the bond length here shows that this is the core part where the defect sits. So wider the bond length here means that there is more change in that bond length. That is how I have represented it graphically. So we see that locally we see a asymmetric change in the bond lengths when boron substitutes carbon in silicon carbide here. And this, if we see for the other cases, aluminum, silicon, nitrogen, carbon, even for the vacancy, we see that this is quite symmetric for all other three cases. That the distortion, although it is more for the cases here that near the defect, the bond length changes more, obviously. However, it is symmetric in all the directions. However, for the case of boron, it is not symmetric and it changes the symmetry. And that whole thing, the changing in the symmetry, basically causes this big effect of phonon defect scattering on the thermal conductivity in silicon carbide. To make a to have a much closer look and understand it in much more detail, what we try to do is understand that what happens if we change the perturbation strength, that V matrix, the perturbation strength. So we see here we have plotted the cross section, which we can easily get from the scattering rate. So we see that the cross section as a function of perturbation strength, we see that for the case of boron carbon, there is a resonance peak at the natural occurring perturbation in that system. And this resonance peak, there are several resonance peak which actually arises because of the poles in the Green's function. So we see that these peaks we can see in the other materials, other defects as well, ALSI and all. However, for the case of boron, it occurs, this resonance peak occurs at the naturally occurring strength of the perturbation, and that's why this resonant scattering is having such a big phonon defect scattering rates, and they are contributing more in reducing the thermal conductivity even with the small concentration of that boron carbon defect. So, so this is the another thing what we get from which we can completely miss from considering these defects as mass perturbations only, because it's the we won't be able to see that resonant phonon scattering if we are just working in the mass perturbations, and these bond perturbations are completely ignored. So I have tried to illustrate with these two examples that isotope scattering or the mass defective scattering is also important in one sense, and then when we have to include the full ab initio calculations and with the bond perturbations also in our calculations, that is also very important for some cases and some materials. So with this, I would like to just summarize what I said. As I said that I have tried to illustrate the ab initio thermal transport in defective materials from two different approaches, considering defects as mass perturbations only. And we see for the case of zinc chalcogenides why they are important and how much effects they have. We have tried to quantify it from that percent isotope factor and how much important it is to have a good correspondence with the experiments there. Then when we consider, there are some cases where mass perturbations are not sufficient and we need more information, and that information is how the bonds are changing in the local geometry is changing when we introduce that defect. And with that, when we see the results, we find very interesting results for this, as I showed you in the case of silicon carbide here, and the boron defect in that case. So this has been implemented in ALMA BT to calculate the thermal conductivity, and we are working with that code here. Other recent works which I would like to highlight here that I've worked on, there is a perspective on these ab initio phonon thermal transport, which we have tried to pull out different methodologies and gather them in one perspective, one document. And then there is also another work in collaboration with Jeffrey Snyder from Northwestern, and it's basically understanding the analytical models of Phonon-point defect scattering in these materials, in different materials. So with this, I would like to I would like to thank you for your attention.
Thank you, Dr. Ankita, for your in-depth presentation. And like participants have few questions arrived from this presentation. Can I ask you now?
Yeah, sure.
S. Jayabhati asking what is the difference between Zeton blend and crystalline nature? That means Zeton blend and Zeton crystalline nature.
What is the difference between zinc blend and
zinc in crystalline nature?
I don't understand actually this question. Zinc in crystalline nature. So,
that means they asked if suppose the zinc is in crystalline form, and how it can be different from Zeton blend.
So the zinc structure is, but we can yeah, for sure
I
find it.
think the question is not well framed. Maybe we can
Okay.
pass on to
Yeah.
other question. Yeah.
Okay. The next question is, if the phonon scattering is more, is it useful for real-time applications?
What kind of real-time applications it could be? Means the speaking. Yeah.
They are generally asking like,
Okay.
so how could it be useful? So whether the phonon scattering is high is useful or it might be low is useful.
So if they want to connect with this real-time applications, with the applications that was mentioning, is basically like electronic applications. So for that, yeah, we need to have, means it's not real-time um, correlation there, but yeah, for those applications we need to have low scattering and high thermal conductivity in that sense. Yeah.
I think one last
Uh,
question, Dr. Manda, you can ask. Huh?
yeah. What is the effect of concentration defects on thermal conductivity?
Oh, that's an interesting question because it has huge effect on the thermal conductivity. Obviously, we take a linear relationship here for our calculations that with the defect concentrations, the scattering strength actually increases. So linearly only. Uh, so this is actually true for the ranges where where the defect concentrations are low. Like let's say low, with low what I mean is basically in the range up to, depending on the material, depending on the defect, but maybe around some let's say 0.01% to 3 to 4%. It could be okay, that linear approximation. However, after that things start changing. If you have very high concentrations of defects, first thing could be that alloy, it will, first thing it will be, and it will be called as an alloy. And with that alloy, the whole geometry of the structure could change, and it may not remain in the parent structure, and then it becomes a different structure. Or maybe sometimes it also could happen that it will just phase separate, and we can get different phases as well. So with defect concentrations, all these things could happen, but here we are in the limits where the parent structure is not changing, and the distortions are not that much that the whole system would completely collapse. Yeah.
Thank you, Dr. Ankita, for your presentation. Now I hand over the session to Madam to conclude the session.
Thank you.
Wow. Yeah. Thank you once again, Dr. Ankita, for such an interesting talk. And on behalf of VIT-CNR, thank you once again for accepting our invitation. So
Thank
it's a
you. Thank you
privilege
for
to have
the
you.
invitation.
Yeah.
Thank you.
Yeah. Thank you. Yeah.
Thank you.
Have a good day.
You
Bye.
too.
Bye. Bye. Dr. Siddharth,